Hello everyone, I'm Simon from the Ubiquitous AI Lab. 2 years before, in the previous IPIN conference, we introduced how we use LSTM and recurrent neural network perform as pedestrian dead reckoning for indoor positioning. So this year, I'm going to introduce our latest research outcome, how we use a hybrid multimodal neural network for positioning using sensor fusion data. Here, we propose an end-to-end hybrid multimodal deep learning localization system called MM-Loc, relying on zero-hand engineer features but learning automatically from data instead. This is achieved by using cross-sensory network structures to extract early features from each sensor modality, which are then combined by cross-modality neural structures. We show that our choice of modality-specific architectures can estimate the location independently. But for better accuracy, a multimodal network structure that fills the features of early modality-specific samplings is a better solution. Our proposed MM-Loc system is tested on cross-modality samples formed by different sampling rates and data representation, including IMU sensors, magnetic, and Wi-Fi signals, outperforming traditional approaches for location estimation. MM-Loc elegantly trains directly from data, unlike traditional indoor positioning systems, which rely on human intuition. We collect a multimodal sensor dataset from two scenarios with ground truth location labels. For training our MM-Loc model, we use two scenarios into a training set, collected from two crowded office buildings. Both scenarios are typical indoor environments with diverse human activities that increase the complexity in terms of noisy data and variation. Here are the trajectory we select to collect the dataset. In scenario A, we collect a dataset containing about 6.8 hours logging information, while in scenario B, we collect 8 hours of the dataset. We highlight each scans of inertial sensor, magnetic, and Wi-Fi samplings on the trajectory. The blue points represent the Wi-Fi logged locations, while the green line represents the sensor's location. As we can see, based on the pointed location, inertial sensors scan at a much faster frequency, while Wi-Fi scans at a lower frequency. Here, the table shows the logged data directly from the mobile phone devices, which contains inertial sensors of accelerometer, gyroscope, and magnetic filter, and also the Wi-Fi fingerprints with ground truth location labels. However, the raw data cannot be directly used for model training. We first need to address the challenges of modality fusion before feeding the dataset into models for training. Specifically, the main challenges include inertial sensors scanned much faster compared to the Wi-Fi scans, which results in imbalanced dataset. The sensor updates on its event base, irregular samplings are logged into the dataset, and modality missing occurs under specific scenarios, which results in a number of non-values feeding into the dataset. It is noticed that the Wi-Fi sampling frequency is significantly slower than the initial sensing rate due to the hardware limitations. For some time step, if there only contains inertial sensor samplings, same as the strategy applied on the missing Wi-Fi, we use -100 dBm to represent missing Wi-Fi scans for all APs. For the purpose of eliminating the sparsity of the Wi-Fi data and to increase the location estimation frequency, we adjust the Wi-Fi scan rate from the original sampling rate to every 100 milliseconds. We take the same data processing strategies as we did in calibrating LSTM on inertial sensors, which includes overlapping rate of 90%, downsampling with time window of 1 second. The table shows the normalized and filtered values. A 1 second time window holds 1000 sampling features from each sensor, a Wi-Fi scans, and a ground truth location. A missing APs in the Wi-Fi scan are indicated with a -100 dBm value. The figure presents our proposed MM-Loc architecture, an end-to-end multimodal deep neural network for indoor localization, which brings in the perspectives of inertial sensors and Wi-Fi fingerprint modalities. The MM-Loc neural network first reads time sequential inertial sensor data by LSTM subnetwork and Wi-Fi RSS data by DNN subnetwork synchronously from the beginning. and both modalities are reshaped to 128-dimensional hidden output from each branch. These two parallel 128-unit hidden outputs are then integrated by concatenation to 256 units. The 256-dimensional joint vectors are fed into three fully connected layers with the input size of 256, 128, and 64, then transferred to the top prediction layer. This operates as a regression, producing continuous value in two-dimensional outputs of x and y from the joint cross-modality hidden layers. What is unique about this construction is that it can handle missing inputs from the Wi-Fi modality. This is because Wi-Fi scans are produced at a much lower rate than inertial sensors. So when there is no Wi-Fi scan available, the input is a vector with all component value of 0, so the Wi-Fi branch of the network contributes little to the cross-modality component, in which case the majority of the contribution comes from the inertial sensor modality branch. When both modalities have inputs, the same multimodal architecture automatically adjusts the weights of cross-modalities to produce estimations based on both modality contributions. The figure presents the comparison between the performances of MM-Loc running at different Wi-Fi sampling frequencies and the single modality baseline models. The results are here presented using CDF chart. The purpose of adjusting Wi-Fi frequency is to assess the impact on location estimation accuracy of this energy-saving strategy of scanning at lower frequencies. It also shows how this would behave on systems where a high refresh rate is not available. We observed that in scenario A, MM-Loc reached a better accuracy of 2.6 meter median precision at an interception point with Wi-Fi model, and in scenario B, MM-Loc performed better than any other models. So, in general, the MM-Loc with the highest sampling rate performed best. MM-Loc median accuracy is within 2 meters error for 80% of the prediction cases, which is 3.5 times better than the sensor baseline model. And another observation is that with decreasing sampling rate, the multimodal prediction accuracy experienced the same trend. We observe that MM-Loc predicts the footpath along the corridor with high quality, having clear estimation boundaries, even though some prediction, especially at the corners of corridors, are over 5 meters away from the ground truth. But in general, MM-Loc accurately predicts the trajectory during the online test under both scenarios. In conclusion, we modeled the traditional method of location estimation from sensor data with end-to-end machine learning approaches. The chosen network avoids the need for canned peaked features. Instead, data processing models are learned automatically from data itself. And secondly, we deploy a recurrent neural network, the long short-term memory, to model the sequential estimation of PDR, estimating a sequence of locations starting from a known point and estimating the following points based on observations from sensor data. And thirdly, we perform modality fusion through a hybrid neural network, using different neural network structures on each sensing modalities and fusing their representations via additional top layers. We use a recurrent neural network for the inertial sensor data processing and a fully connected network for the Wi-Fi modality. Our data-driven fusion approach builds entirely on the quality and volume of data without engineering preliminary features nor making assumptions about the use of the system. With this research, we are moving the efforts from engineering each modality components like step counting, direction estimation, and other conventional integration methods like particle filters, Kalman filters, and graphical-based constraints to a purely data-driven machine learning effort. We believe the proposed fusion approach is extendable to include other various sensing modalities and signal sources, such as vision, sound, and other environmental samplings. Fuse them together, the multimodal architecture will further improve the system performance in terms of the robustness and intelligence. Thank you for listening.